Lagrangians in C3 come in real families of every dimension. That's when I'm ready. So I'm going to be talking about this result, which is joint work with Ian McIntosh of the University of York. There is a preprint on the archive, but I didn't think to write down the number. Maybe I'll come up with that later. All right, so you've heard a lot about special Lagrangian manifolds, but I will give you the definition just as another reminder. Partly I'll mention special Lagrangian with some angle. So the definition is a submanifold say M n of a Calabi-Yau. So this is a Calabi-Yau, so maybe I'll point out twice the real dimension, is called special Lagrangian, and special Lagrangian with angle theta is a slight generalization of the usual definition. If it's calibrated, for the form which is the real part of e to the I theta by the holomorphic volume form. So this is the thing which, since we're in a Calabi-Yau, we know that this is a covariant constant holomorphic volume form. In particular, the things that I'm going to be talking about are not in some Calabi-Yau, they're in complex space. They're actually going to be in C3. But, so in particular, M3, Mn inside Cn, special Lagrangian with some angle theta if it's calibrated with respect to, well, just what I said up there, e to the I theta dz1 to dzn. And another way of saying that, which is really where the terminology comes from, i.e., if its tangent planes are images of Rn under a UN transformation that has determinant e to the I theta, under determinant A is e to the I theta. So in particular, we care about this, the case where it's determinant 1, but we can consider the more general thing. And you'll recall from Blaine's lectures that talking about, I mean, one of the reasons I introduced special Lagrangian with some angle is so that I can state the result that if you have a submanifold, it is both minimal and Lagrangian if and only if it's special Lagrangian with some angle theta. For some theta. We had noted that if something is a calibrated submanifold, it's certainly minimal, and part of the definition of being special Lagrangian is that it's Lagrangian, if you state it in one of the other many ways that we had. But also, you can show this is true by, it's a simple calculation. The mean curvature comes up in an expression for the Kähler angle. All right. Well, I'm going to talk about special Lagrangian T2 cones in C3. And part of the motivation for doing that is that mirror symmetry, and in particular the SYZ conjecture, tell us that if we want to understand Calabi-Yau threefolds better, which come up in supersymmetric string theory, then we should be studying their special Lagrangian subspaces, in particular the singularities of those subspaces that might occur in some family. So it motivates us to study dimension 3, and in particular their singularities. So the singularities of special Lagrangian threefolds in Calabi-Yaus. Now, the local model for these, and the simplest case, the easiest thing you could possibly consider if you want to consider a special Lagrangian threefold, is some kind of cone in C3. So the local model, and the local model is what I'm going to talk about, is a special Lagrangian cone in C3. So that's the subject of the talk. And as we heard in Mark Haskin's talk, and I think we've actually heard this several times this conference, you can study these special Lagrangian cones in C3 by studying special Legendrian surfaces in the 5-sphere. So the correspondence that we have is if we have the cone over some surface, so maybe I should do this with my maps. We have phi mapping from, and this is just the cone, the thing, and have that going into C3, and then the surface over which it is a cone sitting inside of the cone, mapping into the 5-sphere. Well, the cone is minimal. Let me forget about the angle for a minute. Instead of special Lagrangian, say minimal and Lagrangian. So that's going to mean it's special for some angle theta, as we pointed out, precisely when the link, nice annotations, precisely when the link into the 5-sphere is minimal, and the thing that corresponds to Lagrangian is Legendrian with respect to the usual contact structure on the 5-sphere. And you can do more than that. You can get yourself back into something where you talk about symplectic forms and Lagrangian things by taking the Hopf projection down to CP2, and the link in S5 is minimal and Legendrian precisely when this is minimal and Lagrangian with respect to the usual Fabini-Studi metric. All right, so up to congruence, if I have, so I want to just simply say I'm using this diagram to say that studying minimal Lagrangian immersions in CP2 is equivalent to studying special Lagrangian cones in C3. If I have a minimal Lagrangian immersion into CP2, I can take up to possibly a Z3 cover, possibly to a Z3 cover. I can take a cover of that if I have an psi from M into CP2, I can take a cover F of that into the 5 sphere such that the cone over that link is special Lagrangian with some fixed theta, and then I can lift to the 5 sphere. And certainly if I have the special Lagrangian cone, I can simply project down to CP2. So these are the things that we're naturally motivated to study, and these, the minimal Lagrangian immersions in CP2, are something that we can apply integrable systems theory to and describe particular ones of those, the ones which are maps of a torus, using integral systems. There's some description of these completely in terms of algebraic geometry. So that's what I'm going to describe now, and that's the work of many people, actually, but in the form I'm about to write it up, it's the work of McIntosh. It's a theorem was first worked on, to my knowledge, or some result of this form, Sharapov in 91, and then Ma and Ma, Ma is here with us.
Just a question about your previous work.
Yep.
What does the EDI theta in C3 correspond to in S5 or CP2?
It really, I mean, you really just want to say that if you want to say how to lift to S5, you're really just saying the cone over that is going to be special Lagrangian with respect to that theta. Yeah, I mean, you really define it in terms of the lift. So if you take, I mean, you can certainly do it intrinsically. Take F and wedge it with its Gauss map. You're asking that to be a special Lagrangian theta plane. So in the case where M2 is a torus, as Mark actually stated, you can describe this purely in terms of algebraic geometry. So this was done in various forms by Sharapov, looking at maps into the 5 sphere, by Ma and Ma, looking at maps into CP2. The form I'm going to give this to you today, it's the nice, kind of the full version, is by McIntosh in 02. And Hashimoto, Taniguchi, and Otogawa have recently extended some of these results. This form is due to McIntosh. And basically, I mean, I'll write it in inverted commas and then write out the details. But basically what I want to say is that there's a one-to-one, the minimal. This is something I can state in the case when the immersion is simply minimal, and it's something I can state in the case where the immersion is also Lagrangian. So I'm going to put Lagrangian in parentheses. Minimal Lagrangian immersions from a torus into CP2. So basically the theorem says that these are in one-to-one correspondence with some purely algebrogeometric data. So an algebraic curve X, which is called the spectral curve, that comes about as a spectrum of a family of flat connections. It happens to be a 3-sheeted map of CP1, which comes about simply because we're going into CP2, so C3, and a line bundle. Line bundle L over X. And there's conditions. I'm about to state this theorem more precisely. But basically the idea is that you can describe these minimal, possibly Lagrangian, you can put in the condition that means that they're Lagrangian in terms of purely algebrogeometric data. And it satisfies some conditions, the hardest of which, the hardest conditions to satisfy are going to be the conditions that correspond to the fact that the map is doubly periodic, that it's mapping from a torus. It's not so hard to find, especially in the minimal case, but also there, it's not so hard to find things which are maps of the plane, but to make them doubly periodic is a difficult problem, and that the difficulty comes up over here. So satisfying some periodicity and other conditions. So now I'll actually state the theorem like a theorem. And the point is it's a one-to-one correspondence, and you can actually go back and forth. And so you can hope, for instance, to construct some examples using this method, although that has somewhat limited success because the algebrogeometric data gets complicated very quickly. But one thing that you do have at your disposal as a consequence of this is there's going to be a natural invariant associated to one of these maps, namely the genus of this curve. And the examples become more complicated as the genus of this curve increases. You can actually say that more precisely. But for the low genus examples, you get known examples over here. As the genus gets higher, it's not a priori obvious that examples exist, and the theorem I'm going to state today is that examples exist. In fact, there are lots of them. So first I'll state the theorem more precisely. Given minimal and Lagrangian if you want, Lagrangian map from a torus into CP2, you can construct the following data. An algebraic curve X of genus G, but in the Lagrangian case, the genus actually has to be even. That comes out of the proof. So the Lagrangian ones have always got even spectral genus, which is what we call the genus of the spectral curve. A degree 3 map from your spectral curve down to CP1, that you can say something about its branching properties. In particular, it's totally ramified at the points above 0 and infinity. P0 and 0 and P infinity, which is the point above infinity. A line bundle on the curve of degree.
Remember, does totally ramified just mean that there's only one point in the pre-image?
Yeah, that's all I mean. So, yeah, I just mean. And infinity, and of course, I may well have other things in between. So maybe I'll scrap my diagram while I'm ahead. All right. So there's a single point above 0 and infinity. This hasn't actually been worked out for CP2, but it's almost certainly the case that corresponds to the fact that the map is conformal. That's for S3 it's been worked out. I haven't sat down and done it, but that's probably where that condition comes from. It's the condition that your harmonic map is also conformal. So you have an algebraic curve that's a degree 3 cover. You have a line bundle, degree G plus 2, and you have some symmetries floating around. So you have an anti-holomorphic involution on the curve, which covers lambda goes to lambda bar minus 1, so covers the unit. It's so that the real points are the unit circle. If you're in the Lagrangian case, then you have another involution, a holomorphic involution, mu on the curve that covers lambda goes to minus lambda. So the branch points, you've got this three-sheeted cover of CP1. The branch points are necessarily have symmetry about the unit circle. And if you're in the Lagrangian case, then you also have a negative symmetry. And everything in sight has to respect these involutions. So in particular, the line bundle has to respect these involutions. So rho star L tends to L, essentially trivial. This is the ramification divisor. The difference between that and it being trivial is reasonably technical, why you have to use that one. But essentially, it's lambda star bar of L is isomorphic to L inverse, and a similar thing for mu. Ox of R. And have I missed anything else? Yes, there are no branch points on the unit circle. Lambda has no real branch points. By real, I mean real with respect to your anti-holomorphic involution, i.e. no branch points. Points on the unit circle. Okay, right. Now, of course, the point of getting hold of all of this data is that you want to say, if I'm given an algebraic curve with some symmetries and a line bundle satisfying certain properties, I want to know that I can reconstruct the map, and that's exactly what the theorem says. Conversely, given the algebraic data, or the spectral curve data, x, lambda, the line bundle, and some symmetries, as above, you can recover or you can construct, if you prefer, a minimal Lagrangian, if you put in the Lagrangian conditions, immersion. Well, here's the catch, because I haven't actually put in the periodicity conditions. A minimal Lagrangian immersion from R2 going into CP2. Now, if you want to have a map from the torus, then you need to put in some conditions that are going to correspond to this map being doubly periodic. And those conditions are things which you expect to be reasonably difficult to satisfy. So the map at psi is doubly periodic if the algebraic curve data, the spectral data, satisfies some periodicity conditions. If x lambda, if the spectral data if the spectral data satisfies some periodicity conditions, which I'm now going to state for you. Periodicity conditions, and these are fairly stringent restrictions on the curve. So I should say I'm going to give only the briefest idea right now how, beginning with a minimal Lagrangian immersion, you could construct this algebraic data. If I've got time at the end, I'll come back to it. But it's actually much easier to say, if I'm given this data, how I can get hold of the immersion. So hopefully that will suffice as motivation for now. And in doing that, the periodicity conditions come up very naturally. So in fact, your map from the plane into CP2 factors naturally through some object associated to this curve. It factors through something very close to the Jacobian of this curve. It's actually the Jacobian of a slight singularization of this curve, and you have to worry about the fact that since our line bundle was degree g plus 2, we'd better actually be in pic g plus 2. But so in fact, psi factors at our map from R2, and I will write up in non-algebraic geometer language what this means, what this space is. Second, but for now what we're caring about is that this map actually factors, and this one is going to be extremely easy to describe, and our psi is doubly periodic if and only if this map L prime, which I'm going to define for you, which is essentially a linear map. It's an affine map, so it's quite easy to deal with. It's doubly periodic. So to expect you to be excited about that, I'd better define things. All right, so first of all, pick g plus 2 of x prime. Well, the g plus 2 is simply, I'm going to be talking about line bundles of degree g plus 2, which is what L up there was, which means that generically, just use Riemann-Roch, their space of sections is 3, and we're mapping into C2, so C3, so that's exactly the right degree. So pick g plus 2 of x prime. Well, maybe I'll actually define x prime first, although I can do this without defining x prime. So x prime is the curve obtained from x by identifying the 3 points. So one thing I said about the branching data over here, when you're probably wondering why I was giving you so many details, is that it didn't have real branch points. So there's no branch points on the unit circle, so if I'm at a point on the unit circle, there's 3 points on my curve above that. So I'm going to take the points that correspond to lambda equals 1. So identifying the 3 points, let's call them O1, O2, and O3, that are sitting above the point lambda equals 1, to give a triple node. And I will motivate fairly soon why you might actually take the curve and make it singular, why this is the right object rather than the usual Picard. And so
the original X was normal?
Not necessarily, actually. It's probably, certainly generically, and there are no known examples where it's singular. Sasha Babenko has kind of conjectured in other cases just with a parameter count that there shouldn't be singular ones, but it's never rare, it's just a parameter count. So this is the space of degree if you want to think of it in terms of x, which certainly for the things I'm going to use in the proof are going to be smooth. You can restrict yourself to that case if you don't want to deal with all of the ones. Degree g plus 2 line bundles on x together with an identification of the fibres over these points. Identifications, so if we call these line bundles L, together with identifications of the fibres. And I will always actually be thinking about the case when x is smooth, because for all purposes you can pretty much restrict to that case. So that's what this thing is, and it's if x was smooth, then that Jacobian is just some complex torus, and you've got a couple of fibres which are C star. Locally it's complex torus cross C star cross C star. So that tells you what the spaces are. I said that the map L prime was easy, that it was affine, or if it had been mapping to degree 0, that it would have been linear. And it's quite easy to say what it is. First of all, at 0, it gives you the given line bundle. And it's going to be, so it's affine, all I have to do is tell you what its derivative is. So L prime is affine. And I simply need to tell you, if I take coordinate z about here, I simply need to tell you what its tangent is, and I've defined the map. Well, this is intrinsically defined in terms of the geometry of the algebraic curve. It's equal to the derivative of the Abel-Jacobi map of x at P0 with respect to a local parameter, where so zeta is a local parameter of x, or x prime, doesn't actually matter, at P0, where if you cube it, you get your degree 3 map there. Yeah? These are, I mean, I've made a choice. I've taken the...
She's just saying, you're not fixing a metric on those fibers over L. It's actually C stars, not S1s.
Right.
Yeah.
Right.
That's what she's asking.
Oh, okay.
I think that's what you were asking about, whether or not these identifications were done by S1s rather than C stars. She's allowing a C star. It doesn't have to preserve a metric.
I mean, not just the lambda inverse 1 should be any unit number.
I'm not identifying all the points above the unit circle. I am picking a particular point on the unit circle. It's true that I could pick another point, and I would get that would correspond to taking a map in the associated family of the map I started with. But I am just taking one. I'm not identifying along the whole circle. I'm just identifying at a point. Okay. Is that... So, I said, all right, so we have this algebraic curve x. We've identified just 3 points, but 3 points that are all above, one particular fibre. CP1, picking the point 1, O1, O2, O3, and I'm making those a node. I have claimed that the double periodicity of my map, which was something that was going to be hard to deal with, can be expressed in terms of the double periodicity of this map L, which is essentially linear. And to describe L, what I need to do is tell you its tangent. And so I should just remind people what the Arbel-Jacobi map is. So A P naught prime is the Arbel-Jacobi map of x prime with base point P naught. In other words, it's the thing which, well, here I'm going to map into degree 0 line bundles, or if you want, into the space of maps on the regular differentials of x prime, modded out by h1 of x minus those 3 points, z. Or if you'd rather that I express this in terms of x, then I'm just allowing residues. I'm just allowing poles at those points. So to define this map, I have to say, given a point Q, what does it do to a holomorphic differential or to a regular differential? Well, it integrates it from P naught to Q. Okay. So this is something completely intrinsically defined in terms of the curve, and we can express the double periodicity of our map in terms of that. And I said before that this splitting would enable me to fairly simply tell you how to recover the map. So to do that, I'd better tell you what theta is. It's called theta because you can do it in terms of theta functions if you want. But more intrinsically, I'm actually just going to define it on the image of L prime of R2. So for each Z in R2, you can show that these symmetry conditions force L prime of Z to be non-special. And what I mean by that here is just that H1 of it is 0, which by Riemann-Roch tells you that dimension of H0 of L prime Z is the biggest it can be. It's 3. Now, I care about that because that's telling me that H0 L prime Z is basically just a copy. It's just a copy of C3. So that's telling me if I can specify a line in there, then up to identifying the different CP2s, I've got myself the map theta. I've got myself a map into CP2. So you can give a line, turns out, just by asking the sections to vanish a couple of points. So I can also show H0 prime. So this take the sections which vanish. So sections that vanish at these points, P0 and P infinity, defines a line in our C3. We can get ourselves a map to CP2 if we can identify the different copies of CP2. Now, this is exactly why we have to use the generalized Picard, why we have to use the singular curve, because we want to have identifications of the fibers over 0, 1, 0, 2, and 0, 3. That exactly enables us to identify the different copies of CP2. So we have identifications of, all right, so the space of sections of LZ prime, it's isomorphic to the sum of the fibers at these points, we have identifications of these fibres. Identifications of these fibres because we were given something that's actually in the generalised Picard. And so this is naturally isomorphic to just one of these. And then you can choose an isomorphism to C3. I mean, you're just choosing a scaling, and that gives you're getting a well-defined, you don't get a well-defined C3, but you get a well-defined CP2. So that's exactly how you recover the map. Comes through this splitting in a very natural way, and it also gives you a handle on the periodicity conditions. So one thing I want to point out is that these periodicity conditions did not involve the choice of line bundle L. L was just, it's telling you where to send 0. I mean, I can change L as long as I change it to something that satisfies the symmetry conditions. It doesn't matter at all what it is. So the periodicity conditions don't involve your choice of line bundle L. So given a spectral curve, so an algebraic curve X and the rest of the data satisfying the periodicity conditions, you can choose L quite broadly. You can choose L from, well, all L has to do, I unfortunately erased my theorem about the correspondence, but all L had to do was it had to satisfy symmetries with respect to the anti-holomorphic involution, and if you're in the Lagrangian case, then also the holomorphic involution. And what that means is you can choose L from a real G or N if you're in the Lagrangian case. And your G was equal to 2n. Right, so this is the spectral genus. Genus of the spectral curve. You can choose L from a real G or in the Lagrangian case n dimensional family. So this means that if you have one solution, you have many, and the dimension of the family of solutions is determined by the genus of the curve. So it's telling you that the higher the genus of the spectral curve, the higher the dimension of the family that these things come in. So the result that I wanted to mention is, I mean, it's not a priori obvious that there are solutions for each spectral genus. But that's, I mean, we were able to prove that, and then it follows from that that you get many solutions. So theorem joint work with Ian McIntosh is that for each G bigger than 1, or if you're in the Lagrangian case, n bigger than 1, and then G was equal to 2n, there are countably many spectral curves of that genus that give rise to minimal, and if you're asking Lagrangian Tori, countably many spectral curves of genus G or genus 2n giving rise to minimal, if you ask for it, Lagrangian emergence of a torus. some torus. We can't actually fix the conformal type of the torus. It's some torus. It's not that you can fix the conformal type and then have many of these. It's interesting to ask actually what the conformal types of the torus can be. So then, from what I just pointed out, an immediate corollary of that is that for each g bigger than 2, n bigger than 2. All right, so over here I should say, okay, you can choose L from a real, let's just be sane and talk about the minimal case, from a real g-dimensional family. You might say, well, that gives you a real g-dimensional family worth of minimal immersions of the torus, but you chose a point 0 in the torus when you did this correspondence. If you mod out by that, then you've got to take 2 away. So for each g bigger than 2, there are countably many g minus 2 dimensional families. Minus 2, n minus 2 dimensional families, dimensional real families of minimal Lagrangian immersions of tori. Minimal Lagrangian tori in CP2. So the family comes for you for free because of the method, because we're using this integrable systems method. But you have to do some hard work and prove that there are some. Now, it's actually natural. And why should there be countably many? It's natural because this periodicity condition that you're asking for, it's a rational condition. It's a rational condition. You're actually, when you, I've erased the thing that I care about, but when you take your L prime, you're actually not just mapping into the Picard, you're mapping into a real subset of that because your line bundles have these symmetry conditions. So you've got a rational condition in a real space. And you expect countably many solutions. So let me say that in some form. So back to the periodicity. So I'll give some outline of the proof is what I'm going to do. So the periodicity condition, by the time we factored through this L prime, remember we had R2 going to L prime, going to the Picard group of the singular curve, going to CP2. The periodicity condition was that L prime was doubly periodic. And to also remind you, the thing which defined L prime was, we said what its tangent is. Abel Jacobi P naught d by d zeta. So we have to look at this. This is the thing we want to be doubly periodic. D's, differentials. So what we care about is we're interested to know what we want is that this plane, naught of x prime at p naught, we want this plane to be a rational plane in the Jacobian. Okay? And that's a double periodicity condition. Well, let's restate it so that the dimensions are actually a little bit nicer. We have these symmetry conditions, and that's actually going to mean that we're not going into the whole Jacobian. We're mapping into a prim variety, the real part of a prim variety. So we actually, I can, instead of asking it to be a rational plane in here, I can ask it to be a rational plane in the Primian. In other words, the set of all line bundles L with the symmetries that I wrote up before that L had to satisfy. I'm going to forget the ramification divisor for now, because I only have space for this, and it's unimportant. So this thing, line bundles satisfying degree 0 line bundles, satisfying these conditions, I mean, it's line bundles satisfying some reality conditions. This space is dimension is dimension R to the G in the minimal case, R to the N in the other case. So make sure I haven't forgotten any of the things I wanted to say. All right, so we want to see that this plane is rational. Oh, actually, I'm x prime n plus 2. Sorry about that, because I've taken the identifications of the points, so I've got an extra 2 things. Okay. So to define what that thing is, you just need to look at the Arbel-Jacobi, Arbel-Jacobi map and see what the image of this plane is. Well, the Arbel-Jacobi map, the thing we wrote up before, from x going into the Jacobian of x prime, what does it do? If we want to send q to, this is just what I wrote up before, the integral from p0 to q of omega. So if we want to know what we want to compute the derivative of this thing, d by d zeta, so that is going to send omega to p0, so d by d zeta of the integral from p0 to zeta of omega. And what's that? Well, that's simply the residue at p0 of the differential omega divided by zeta. And I'll just use the notation omega of p0 for that. So what if you pick a basis for the regular differentials, so omega 1 up to omega g, but you're allowing simple order poles at these extra points. So you've got 2 extra of these. We're asking the plane that's the span over the real numbers of the real and imaginary parts. So let's write the whole basis like this. The real and imaginary parts of this derivative, imaginary part of omega at p0, to be rational in the Grassmannian of 2 planes in R to the G. So that's the periodicity condition. And we have to show for each g that there's some point where it's satisfied. Well, the point actually is that you can use the inverse function theorem to do this. That locally, at least, the space of parameters that define your algebraic curve data, your spectral curve data, has exactly the same dimension as this Grassmannian. And so you can run an inverse function theorem argument. Well, if we're going to try to run such an argument, and that's how we get countably many solutions, to run such an argument, we need a point about which to run it. We need a point at which to show that the map that takes us from spectral curve data to this plane, and I'll give the plane a name, has to have invertible differential at some point. So we need some natural point about which to do the argument. Well, there is a natural degenerate case. So the degenerate case is when the branch points come together on the unit circle. So I'm running the argument for the minimal case, but I just have to put in the extra symmetry to get the Lagrangian case. So the degenerate case is when you have pairs of branch points like this. Now, locally, you can take about this point. Now, this actually doesn't correspond to a minimal torus. Remember, the branch points weren't actually allowed to come together. But about this spectral curve, so about the spectral curve defined by the data that all the points come together on the unit circle curve, you can define a family of curves parameterized by angles theta 1, so the angle theta 1 to theta g of where you've asked the things to come together, and some parameters t1 to tg which measure, now it's not really the distance, but you'll forgive me if I write it like that, but some parameter that measures, we're pulling these apart from the unit circle. So some parameter that measures where they are in the unit circle, some parameter that measures the fact that we're pulling them apart. And so this is just given by, i.e. by an open set in R to the 2G. And then the observation that tells you what the work is that you have to do is that what you need to do is show that the map from this open set to the Grassmannian. So then you show that the map that takes you, let's call this open set U, the map that takes you from U into the Grassmannian of two planes in R to the G, that takes you from your points theta 1 to theta g, t1 to theta g. So that corresponds to some spectral curve, x, takes you from there to this plane that we talked about, that's in this Grassmannian, show that this map has invertible differential. At some point on the unit circle, at some theta 1 to the theta g. Okay, so that's the work that you have to do, and if you're interested in the details, then I'll send you to the preprint. So thanks very much for your attention. if you move the line bundle, you're not changing the conformity.